So let's take a look at the graph. I'm going to switch my view here and pull up a picture of the graph that I've got ready to go. You'll see that I've graphed the same function expression that we see on our paper. And if we were to put our cursor here, we can let our cursor drag closer and closer to where x is 1. We can do this from both sides. And notice when we get there, there's actually a hole and the function value is undefined. But if we look at the values as they get closer, we can see that the values of the function are approaching -2. Let me switch back to our other camera view here for a moment. So we're going to say that from the graph, it looks to us like the limit as x approaches 1 of this expression is actually equal to -2. We'll worry about more algebraic ways to do this later. All right, here we have an important problem for trigonometry. This is a difficult problem to do algebraically, but we can certainly rely on the graph. If we try plugging in our value, which is basically going to be our first step regardless, plugging it in, the sign of 0 is equal to 0, and the denominator will also be equal to 0. So we're back to a case that we don't have an answer for with the direct substitution rule. So we could go back to the graph of this one, and I'd like you to pause the video for a moment, pull up desmos.com/calculator, type in sin x over x, and look at the graph yourself. And if you took a chance to do that, you can see that from the graph, it looks like the limit as x approaches 0 of sin x over x is equal to 1. So we're going to give this informal definition of a limit. We say, so here we are using the language, the limit of f of x as x approaches a equals L. Here A is considered to be an input and L is considered to be a value of this limit. We say the limit equals L if the values of f of x get closer to L as the values of x get closer to A. Now, when you read this information, I want you to be thinking about the values getting closer to A as meaning like we did on our first picture. We're moving along the graph side to side towards that value of A, and we're looking at what the vertical value of our fingers is doing. They should be converging towards one another, and the value that they converge to, that would be our limit. We're going to add a little asterisk here for some of the fine print. And what we say here with the fine print is that the values must be approaching from both sides. All right, the x values approach the number A from both sides. And one more parenthetical note right here is, while the values are getting closer and closer to A, they never have to reach A. And it's that idea of never reaching A that lets all of the pictures on our first page count. So if you think about it, as long as we don't ever let ourselves get to 8, then these three graphs are identical because the only place where they're different was when you actually reach 8. But the approach towards 8 was the same, and in all three cases, the output values get closer and closer to 1. All right, let's take a look at some limits that are one-sided. So in a one-sided limit, we don't have that condition of approaching from both sides. we're looking at the two sides individually. Let's start in part A. Where is the function broken? We can see that the function comes down with this little loop, has a little break, and then continues. There's another break, and it keeps going. So I see that the function is broken. By the way, where is a reference to the inputs. It's broken at x equals 1, and then again at x equals 4. Evaluate if possible. This function's name is g. G of 0 means the output value of the function when 0 is the input value. So g of 0 is a reference to this point. Input 0, output 3. G of 1 would be a reference to any point that has 1 as its coordinate, and there's a point. G of 1 is 2. And G of 4, there is no point above 4, so G of 4 is undefined. Now, when it comes to the limit, at each of those same input values, 0 and 1 and 4, we need to approach from both sides and then state the output value that the graph is getting closer to. Now notice for 0, on this left branch of the graph, it swoops down like this, and as we approach 0, it's coming towards 3. If we go just to the other side, it's also coming towards 3. In fact, we could say the graph is unbroken at 0. So our key concept on the other page says the limit is equal to the function's value. The limit equals 3. Let's note that it is continuous. In the case of 1, now we're looking at this point where there's a break. And if we look at the limit as we approach 1 from the left side, the values are coming up toward here. That looks like about 3.5. But if we approach from the right-hand side, we are not approaching 3.5, we're approaching 1. In a case where the left side and the right side are not approaching the same value, we say the limit does not exist. We'll use this 3-letter abbreviation, DNE, for does not exist. And what's happening here is the graph jumps. In the last case, is we're approaching 4 on the left side and on the right side. We can see in both cases, the graph appears to reach a height of 2. So let's say the limit is 2. And we notice that it's broken, it has a hole. But like our first example, the hole wasn't a problem in terms of determining a limit. So let's get into a little bit more detail about the one-sided nature of this graph, especially when x equals 1. So let's say up here, I left a little blank for us to fill in, even though the limit, oops, I'm calling it f of x, but it's really called g of x, as x approaches 1 does not exist according to the definition. That is to say, the two sides don't approach the same value. We see that limit-like behavior exists on each side. In other words, if we didn't have this half of the picture, in fact, I'm going to be so bold as to just erase this half of the picture. And if this is all we were looking at, we would be looking at the limit as x approaches on the left side of 1 as approaching maybe 3.5. And this is the notation that we'll use for that. As x approaches 1, we want a way to say from the left, and we will put a little superscript up here as a minus sign to indicate we're approaching from the left. As that happens, the g of x values are approaching 3.5. Make sure that looks like a decimal point. And we can write that with this formal notation. The limit of g of x as x approaches 1 from the left, notice that little insertion there, is 3.5. And then over here on the other picture, let's consider what happens as we approach 1 from the right-hand side. So I'm going to get rid of this part of the graph. I don't really need to get rid of it. I just don't really want to be looking at it. So here we're looking at the approach in this direction from the right-hand side. And we can say that as x approaches 1, we'll use a plus sign to indicate we're approaching 1 from the right-hand side of 1. Then g of x approaches 1. In other words, as we get close to x as 1, the y's are getting closer to 1. And we can write the limit as x approaches 1 from the right of g of x is equal to 1. We refer to these as one-sided limits, and these are technically not real limits because our definition said you have to approach from both sides. But it's common in calculus to use the notation of something like a limit, even when it's not technically a real limit, just because it gives us a way and a concise mathematical statement of describing the behavior.